All right, so this is a continuation from yesterday. And yesterday we just talked about centripetal force, centripetal acceleration, and problems dealing with that. So as a quick recap, centripetal force is a force that's the net force moving towards the center of a circle. Centripetal acceleration is the acceleration towards the center of the circle. And I gave a couple equations that had to do with that so that you can solve it. Where is my completed notes? Here we go. So we're just going to look at some more complicated questions carrying on from yesterday. So what is this? We saw horizontal circles. Today we're doing vertical circles. So yesterday it was all about if something's moving in a horizontal circle, what are the forces acting on it? Now we're doing vertical. So suppose this is a mass attached to a string and it's now doing a vertical loop like this. We want to look at what are the forces acting at the top, what are the forces acting on the bottom. So basically, what's the free body diagram at these 2 points? So at the top, what forces do I have acting? Force of gravity is what direction? Yeah. What else? Yeah, but on a free body diagram, we don't draw motion, we're just drawing forces. So what other force is acting in this case? Tension. And what direction is tension? Also down. So at the top, I've got two downwards forces, tension and Fg. If I look at the bottom, what are my forces there? Yeah, so I've got force of gravity and tension, but force of gravity is always downwards. Tension is now towards the center. So my tension flips depending on where in the circle I am. And then you get the weird ones where it's on the side, where you have tension going this way, force of gravity downwards. We tend to just deal with what's at the top and the bottom. I haven't seen a question yet that dealt with one in the middle. So as with any object moving in a circle, so there is a net force that is acting in this case. As I said yesterday, the net force is what our centripetal force is. Force centripetal is just the net force towards the center of a circle. So we've got net force acting on it. Let's change that to a comma. Towards the center of the circle. So that's going to be a commonality in all these questions. There's always going to be some net force towards the center of the circle. As I said, the net force is the centripetal force. So notice at the top, what would be my force centripetal equation for this? Just based on the forces. Yeah. No. Yeah, these two are going to be added. When we're at the top, they're both moving towards the center. So they are both towards the center of the circle. So you add them together. As opposed to the bottom, so if I'm looking at the bottom of this, I need the force towards the center of the circle, tension, minus the force away from the center. So this should seem a little bit familiar to you. It's just the new context of Fc. But Fc is just what's the net force in this case. Any questions on this? Okay. Is there more in that box? No. So now suppose the mass is just is spun with just enough speed to keep it in a circular path, as in you just barely are spinning it around and it's just barely making it over the top. Any guesses what's going to happen to the tension in the string?
Well, I think the total tension will be over this.
Will be what, sorry?
It will be smaller than...
Smaller? Yeah. And so what would be the smallest amount of tension we could reach? 0. Yeah. So the tension at the top is going to be 0. This is if I'm moving with just enough speed. So this is a very common question in the practice problems. This is a very specific case where the tension at the top is 0. Can we ever have that the tension at the bottom is 0? Yeah, just look at this equation. Fc always has to be positive, otherwise we don't have a circular motion. So I have to have some tension that's at least as big as Fg, if not bigger. Or no, it has to be a little bit bigger so you keep in the circular motion. So we say at the top the mass is weightless because the net force working on it is only the Fg. This is not in my notes, is it? No, there we go. The net force working on it is only gravity. So essentially it's the same as being in free fall. So you can do this. If you have a bucket of water, you can spin it with a certain speed so that when you spin it around in a circle, the water doesn't fall out. So you just need to be spinning it so it's faster than the force of gravity. Otherwise, you'll get wet. So let's try a practice problem. So we've got an object going in a vertical circle. We want to know what's the minimum speed of the object at the top for it to remain in circular motion. So this is our special case. So if this is what's happening here, so we've just got Fg. So we will say the force centripetal is equal to Fg. Because we have no tension in this question. So then, let's see, what are we given? We're given the radius, we're looking for speed. So the equation we'll use for Fc is going to be mv squared over r. Fg, we have this, it's just mg. We're not told the mass of the object, but that doesn't matter because the masses cancel. So therefore, I get v is equal to the square root of rg, and we have those values. Right, rg square root, yep, perfect. And you just plug in your numbers, you'll get an answer. Questions on this? Okay. So you'll be dealing with the Fc equation a fair amount. Lots of times the masses cancel out. You'll be good with this. I figured you guys are good with that. So notice, notice that this should be if. Notice that if the velocity of the object is constant, this shouldn't say velocity, this should say speed. So if the speed is constant, which in every case that we're going to deal with it is, it only depends on two things. It's going to depend on the radius and the period. So this is alluding to our equation we had yesterday, v equals 2 pi r over the period. What's that? Yes, yeah. So we got this from speed is distance over time. If we look at one complete circle, the distance traveled is 2 pi r, and the time to do one complete circle is the period. No, it has to be the radius here. So you'd have to divide it by 2. So in the case, whenever you're finding something that's a minimum speed for an object at the top, we've got this equation. So Fc equals Fg, and because of this, you get the velocity is equal to the square root of gr. That's just a special case that's used often enough that it warrants having its own special equation. Good with this? So let's try a different one here. So we've got another object going in a vertical circle. We're told the time for one revolution. We want to know what's the tension at the top and at the bottom. So we're just going to use the equations that we looked at before, in that on our circle, if we're at the top, we've got tension down, we've got Fg down, as opposed to the bottom, Fg is like this, tension's like this. So depending on which situation we're dealing with, we have a different Fc equation. So at the top, Fc is equal to tension plus Fg. So since we're given in this question the radius, because the length of the string is going to be the radius, and we're told the period for this. So for Fc, we're dealing with m, what is it? M4 pi squared r over t squared, I believe. It shouldn't be r squared. Yep, that's right. You can tell outside of this unit you don't use this equation much because I never remember what it is. So this equals tension plus force of gravity, so that's just mg. Notice here the m's do not cancel, so you cannot always assume the m's will cancel. And then you just need to solve for tension. So we have all the values for this. We know tension is going to equal mass, so 1.7 times 4 times pi squared times the radius, which is 0.6, over the period, 1.1 seconds, all squared, minus mass 1.7 times 9.8. And then we'll get a number for this. It'll be 17. This is just from yesterday's notes. This equation comes from yesterday's notes. So you don't need to know where it comes from. I derived it yesterday. So we're going to do the same thing at the bottom, except change the equation around. So Fc is tension minus Fg. So we're going to do the same thing, except tension is Fc plus Fg. So we're going to do the exact same thing, except with a plus sign. And in this case, we get 50. So Fc is going to be this, and Fg is going to be this. So I'm doing the exact same thing except with a plus sign instead of a minus. It should look very similar to the elevator type questions. It's very reminiscent of that. Any questions with this? So that is a vertical circle. Now we're going to look at something called a banked curve. Yesterday we looked at unbanked curves. Today we're looking at banked curves. So when cars travel on high speeds at the highway, so it's not just friction that keeps them around in a circle. So if it's an unbanked, it means that it's level and you're turning around a corner that's level. And so you've just got friction pulling towards the inside. But if you see stuff like NASCAR races or, what is it, the Nuremberg Ring in Germany, where they do their testing of different race cars, any sort of steep curve is often somewhat banked. So it's at some angle to help you turn a lot quicker. So we are going to consider what this looks like in order to complete a circle. So what you're going to imagine with this is curved up so that I can move in a circle like this. So we're looking head on at the car, and we need to figure out what this looks like. So if the car is coming out of the screen, we're going to look at this case with FG, and we've got F normal. So this should be familiar. You should recognize where this comes from. The problem is in the past we've done this as parallel and perpendicular. We're not going to do that this time. Just to mess with you for once you get to the final and you see this in multiple cases. We are not going to deal with that. So notice here, it's frictionless. So we're not going to talk about friction. On a frictionless corner, we've got only Fn and Fg are acting on the car. Note, so Fn should be larger because it does two things. It first matches Fg because you cannot be accelerating into or out of the plane, and it's going to, because of both, and accelerates to the center of the circle. I'll just put center. So the normal force is what's causing this car to actually go around the curve. There's no friction that's holding it. So essentially what I've got is I've got this component and this component. So this one is equal to Fg. This portion here is what's actually causing us to accelerate towards the center. Can you picture what's happening there? Because I know sometimes the drawings for this are a little confusing. I think, do I have an animation for this one? I've seen them, yeah. Mm-hmm. Yeah, it's because they have to go fast enough to be able to go around those. So this one, if it works. So this is a little animation showing a car that's going around an unbanked curve. So there's no curve going on. So just at the different angles, this is what it looks like. Notice here, the friction is always going towards the center of the circle. And you've got your normal force and you've got the weight down here. So that is unbanked. Now you can imagine with a banked curve how that changes. Do I want that? No. I don't think I have any more videos, no, of the banked curve. So if I add these two things together, the normal force and the Fg, this is going to be our force centripetal. Because again, force centripetal is the net force. Net force is adding all the forces together. So in order to solve this, I'm not breaking this up into perpendicular and parallel. I keep it as xy. Again, I could split it up. It's just going to get confusing. Because my centripetal force needs to be to the right, so I want all my forces to be up, down, left, right. We're doing x and y. Yeah, not perpendicular and parallel. So let's try this question. So we want to know what angle does our curve need to be so that a car can go around it safely at 22 meters per second if this is the radius of the circle. One is talking radius of the circle, so if you imagine a car is traveling like this and then it curves like this. If I kind of give an extension of this curve to give you a circle, that's what it means by a radius of a curve. So just assuming if this curve were to go all the way in a circle, what would it look like? So let's draw this out so we can visualize what's happening. So here's our banked curve. Here's our car. We've got an FG going down like this. Please silence your phone. So that... Hi, can you turn your phone on silent, please? Thank you. Here's our FN. And we're going to deal with this. Like I said, we need to break up our situation as such. So we're going to break this up into, oh, my computer's going to freeze for a sec. We're going to break up Fn into its x and y components. We'll give it a sec. So in order to figure this out, what do we need to do? So our FC is going to be just this x component of the normal force. So I can do this by breaking up the normal force into its x and y components. That's one way you could do it. And again, that's your component method. Or I can do this with the trig method and go Fn, which goes up and to the right, plus Fg, which is going down, will give us Fc. So either way you want to go about doing this, it'll work no matter what. So I can do it this way and say, here's my two components, and saying this portion is equal to this portion, and therefore I can solve for what my angle is going to be in there. Or we do trig. I'll show both. So for Fn, we've got this. So I just said this side is equal to Fg because those are equal. So Fn in the y component will equal Fg. We can solve that. Just mg. Do I have the mass of the car? Ooh, okay. So let's just keep it as m times 9.8. Then this part here, this side is going to be F normal in the x direction, which is equal to Fc. This is our total centripetal force. I'm told the speed and the radius. So in order to get the force, we need to use mv squared over r. Again, we don't have the mass, so let's just leave the mass as is. We've got the velocity squared, 22, over radius, like this. And this is going to help me to find the angle. So if you remember the issues with trying to figure out the angle, we want to know what this is. Now it's just a matter of figuring out which angle is it here. And this is going to be where it gets complicated. So there's a, oh, how can I do this to explain it properly? Let me draw this bigger so you can see it. So essentially what we've got here's our Fg, here's our normal force, and I'm going to draw it out like this so I can see it better. So if this is angle theta, using my Z rule here, this is angle theta. If this is angle theta, you know inside here is 90 minus theta, which tells you this is theta. If that doesn't make sense, probably using the trig method is going to make a lot more sense solving this one. So this is what I'm looking for is this. And in order to solve that, I need extra space. So we're just going to use tangent. So theta, oh, not again. If you do tangent, so tangent's just opposite over adjacent, you'll notice that your masses will cancel out in that case. So then you'll just be able to plug that in and be able to solve it. So even if you aren't given a variable, at some point it's going to cancel out, or it should. Yeah?
And I always assume that when doing this theta is top-ended, and y and x.
Yes. Yeah, you can always assume it's that top one if you want, rather than always the top one, yeah. So theta equals the inverse tan of my opposite. So opposite in this case is fnx. So m22 squared over 475 all over the y, which is m 9.8. Masses cancel, and you get theta equals 6 degrees. So here's one of the cases where the component method is more tricky. That doesn't happen very often. So let me show you how simple this is when I'm dealing with adding this in the trig method. So if I just add these together, I'll have Fn plus Fg equals Fc. So you're going to have a very similar kind of equation for this. Again, we're solving for this upper angle, so you'll notice it's going to be very similar. Actually, the exact same. Why did I think that was going to be easier? Yeah, because from this we can just go straight to this and say theta equals the inverse tan of the Fc over Fg. And then just plug the equations in there. So it's actually the same in this case. Questions with that? It'll take a little bit to get used to which coordinate system you're using, stuff like that. A little bit of algebra thrown in there. So let's try this. We've got a plane on a string. Did any of you ever have a toy like this? Yeah. I never had one either. I just remember it from Toy Story, that's about it. So this is what we've got, but it's a similar situation. So if I look at the plane, here's our Fg. Here's our tension. So instead of normal force, now we've got tension. And what is it asking for? What is the period of rotation in this case? So we know we're going to do with Fc. Let's just break this up into components because we know that what this is going to be. So here's tension. We can break this up into its two components. This is going to be Fc, or equal to Fc. This is going to be equal to Fg. This is not technically how it should be, but we'll do it like this. We can calculate Fg, right? We can calculate Fc. We don't really care what tension is, so we don't need to solve for tension. And that's the most convenient part of this. We know this is 28 degrees. So in order to solve this, we've got tan 28 is equal to the opposite, Fc, over the adjacent, Fg. And then we just need to solve for a period in the Fc. So I'm going to make this a little bit easier. I'm going to put FG over here first before substituting. So FG is just mg times tan 28. FC, since we're looking for the period, we want to do this m4 pi squared r over the period squared. Again, masses cancel. Even though you're given it, you don't need it. We know g. We know what the radius is, right? Yeah. So now it's just algebra solving for the period. So I'm going to assume that you know how to do that. And we'll get tension, or sorry, not tension. Time, in this case, to go one complete rotation, 2.5. So here is where it's going to start getting tricky because we've got two capital T's. Tension, period. This is the only case where that's going to hopefully occur. Questions with that? I think that's it for this lesson. Yep. So that is that. How many sections do we have left? We only have 3 sections left in this unit. It'll be done by Wednesday. It's going to go really quick. And if you have not had a chance to look on Google Classroom for the schedule for the unit, make sure you check that out so you know what's coming.